Can you listen me?
Okay, I'm hearing
Okay.
you. And please,
Hello.
Full screen sharing, please. Could you do now? Is it Word? Yeah, this is okay. Okay, the link and other facilities for the online presentation seem to be okay. It is a really great pleasure for all of us to have here Professor Gokcan for the noticeable talk on an investigation on the vertices of FUN obtained from Lucas numbers in hyperbolic geometry. Professor Gokcan, do welcome to your presentation, please.
Thank you. Can I start?
Of course.
Thank you. Hello, I am Ibrahim Gokcan. I attend the webinar from Artvin Çorlu University. I thank TÜBİTAK for giving me the chance to present in the webinar. The name of our work is an investigation on the vertices of a field obtained from Lucas numbers in hyperbolic geometry. In this presentation, we gave some historical information about non-Euclidean geometry and graph theory. We investigated elements of graph theory in hyperbolic geometry. We optioned a value of vertex with Lucas numbers and some identities which related to these numbers. Fibonacci and Lucas number sequences, we know that the Fibonacci sequence is known as 1, 1, 2, 3, 5, 8, 13, and it continues like this. The name of the series was given by the French mathematician Lucas in 1876. The recurrence relation is defined as in the equation. In other words, we say that the sum of the two consecutive terms gives the next term. The Lucas sequence is known as 1, 3, 4, 7.
Professor Gokcan, sorry, I am interrupting you. We couldn't see the slides. Could you please press F5?
I don't understand.
F5, F5.
Pardon.
Could you please press F5? Hocam oradaki başlat mı var? Ona da basabilirsiniz.
Hocam F5'e bastım ama oradan
görünmüyor değil mi?
İyi hocam ya. Tabii kaç tane bastım ama hatta yine basıyorum.
Hocam slaytları değiştirerek gitmelisiniz. You should change the slides. Maybe by clicking.
Şu anda görülebiliyor mu hocam?
Sadece ana sayfayı görüyoruz hocam.
Peki hocam ben bunu Word'de PDF'e çevirsem görülür mü acaba tekrar?
Hocam mouse'la bir tıklar mısınız hocam? Bir sonraki slaytınızı görebiliyor muyuz? Mouse'unuzu bir tıklayın.
Tıkladım hocam. 2 defa tıkladım hocam.
Yok göremiyoruz hocam.
Hocam istiyorsanız PDF'e çevirip oradan anlatayım.
Okey. O zaman bir sonra sizi alayım hocam ben.
Tamam.
Hocam,
tamam hocam ben bunu bekleyeyim hocam o zaman. Bir sonraki soru
Sayın
için.
hocam, ben Murat hocam. Birden fazla sunum açmış olabilir misiniz? Yanlış sunumu
yanlış ekranı paylaşıyorsunuz. Evet hocam.
Şu an kapak sayfası görünüyor şu an.
Biraz evvel değişti hocam.
Şu an gelmedi galiba.
Hocam yön tuşlarına bir basın. Yukarı aşağı. Yani ikinci ekranınızda var galiba hocam. Bir ekranınız daha var mı?
Hocam ben tek bağlantı yaptım ama.
Şu an göremiyoruz hocam onu. Hocam sharing'i kapatın isterseniz bir sonrakiyle devam edelim.
Hocam.
Sizi en son alayım ben.
Şöyle bir şey yapsam olur mu hocam? Başka bir PDF versiyonu var ama ondan alsam olur mu acaba? Farklı versiyon var.
Olur hocam.
Bir dakika hocam. Bunu kapatayım.
Önce sharing'i kapatın hocam.
Bir dakika hocam. Şu an görülüyor mu hocam?
Evet hocam. Ctrl L yapın.
Kontrol et.
Full screen.
Şu an görünmüyor değil mi hocam yine?
Okay.
Şu an görülebiliyor mu hocam?
Görünüyor hocam.
Tamam, o zaman devam edeyim hocam, eğer sizin için de müsaitse eğer.
Okay.
The Lucas sequence is known as 1, 3, 4, 7, 11, 18, and it continues like this. The recurrence relation is defined as seen in the equation, such as the Fibonacci sequence. Hyperbolic geometry, Euclid is known as the founder of geometry. The geometry created on the postulates in the elements he wrote in Alexandria in the 300s BC has been studied for years. It can be said that the word postulate corresponds to the word axiom today. The word axiom is used for propositions that do not need to be proven, but which we can observe to be true. The word axiom has a general usage, and the word postulate has a field-specific usage. Euclid's first four postulates are easy to understand. The fifth postulate is more difficult to understand than the others. Proving this fifth postulate occupied mathematicians for a long time. Knowledge progressed cumulatively. In the Middle Ages, elements books were translated in the Arabic in the Islamic world and studied by Muslims for many years. And commentaries were written on the works for the book. One of the concepts studied in the Islamic world was the concept of infinity in the fifth postulate. It was in the 18th century that studies on Euclidean geometries came to the fore, again after a long time. Girolamo Sacchari is accepted as the founder of non-Euclidean geometries. Girolamo, by putting forward the hyperbolic parallel postulate, tried to prove that this postulate was in conflict with the first four postulates, and thus tried to show that the fifth postulate was correct, but his studies were inconclusive. Studies on Euclidean geometries began decrease in the 18th and 19th centuries in the Western world, especially Carl Friedrich Gauss, Nikolai Ivanovich Lobachevsky, and Thomas Bolyai conducted studies on the subject. The acceptance of the new geometries was not easy. In such geometries as Euclidean geometry, they had to be consistent within themselves and give answers to the questions that Euclidean geometry answered. The existence of elliptic and hyperbolic geometries, for which the fifth postulate was not true, aroused serious suspicion agents of the light truths in mathematics. Poincaré and Beltrami worked on the visualization of hyperbolic geometry. The Poincaré circle model and the Poincaré upper half plane model are the most common modeling examples used to represent a hyperbolic plane. Graph theory and elements defined on hyperbolic geometry. It is generally accepted that graph theory started with an event based on the ascent of people to Goros according to a certain route over 7 bridges built on the Prega River, which passes through the town of Kaliningrad in Belarus. The event is to test whether it is possible to reach the same corner by starting from any corner and crossing the bridge only once. Swedish mathematician Leonard Euler brought the subject to literature with his work 7 Bridges of Königsberg published in 1736. However, the first examples of graph theory can be traced back to the works of Pythagoras and his students. The Pythagoras admitted that there are only 5 smooth objects. As a result of planar expansion of these 5 regular objects, vertices and edges connecting the vertices are formed. The result is planar simple graphs. Graph theory has focused on different problems over time. One of them is the color problem. In the following years, graph theory began to be studied on the hyperbolic plane. G1, F1, and especially Fourier graphs are defined. From here, starting from infinity, the values of the graph at extended numbers are considered as vertices. The hyperbolic geodesic consisting of the lines perpendicular to extended numbers between the vertices and semicircles whose center is on extended numbers are considered as edges. You can see a diagram about circular triangles created with the first sequences with these vertices. These are vertices and these are edges, and we let these edges as hyperbolic geodesics. Suborbital graphs. Graph theory is defined on this set with for these elements. The orbitals of this transformation are called suborbitals of G. O alpha beta represents the suborbital graphs alpha beta. The suborbital graphs G alpha beta can be obtained from the suborbital O alpha beta if this exists with gamma and delta vertices being elements of extended rational numbers. The orbit represents a directional edge from gamma to delta and is denoted by this. This edge can be drawn as a hyperbolic geodesics. We know that Möbius transforms are represented with elements of modular groups. The modular group is section group. In particular, if the modular group is denoted by gamma, it is written as. And in other words, we can show gamma with this set. Gamma 0 and a subgroup of gamma, and we can show with this set. The moment of gamma on extended rational numbers is transitive. Therefore, each suborbital contains the pair for this. If these conditions are provided, we denote the suborbital by ON and the suborbital graphs corresponding to the suborbital as GN. F1 is the subgraph of GN consisting of the belong if. Thus, GN consists of discrete copies of F1. If these conditions are provided, we can say this graph is right directed. And if these conditions are provided, we can say that this graph is left directed. In addition, gamma 0 and transitively parameters the vertices and edges of F1. Lemma. If this is provided, there is an integer k that satisfies the congruous equation. For these values, this matrix, which the element of an equivalent subgroup of the modular group, connects the vertices respectively on an infinite minimal length path in suborbital graphs F1, and each vertex form a continuous fraction structure. Continuous fraction, a continuous fraction is defined as, this continuous fraction can be written as, however, nth approach for continuous fraction is denoted by Fn, and it is written as recurrence relation. Let the nth numerator of the continuous fraction be Pn and the nth denominator of continuous fraction be Qn. Recurrence relation can be defined as with initial conditions. If we take these values in this recurrence relation, we take this recurrence relation. Nth value of the continuous fraction can be written as, and we know that Möbius transforms are represented with elements of a modular group. If we take k equality 0 in this equation, we find this vertex. And if we take k equality infinity, we find this vertex. If this recurrence relation is examined, we optioned these equations. In particular, if this is applied in the equation, we found this equation for k greater than 2. If the equation is solved, we found Pn as. In particular, if we take k equality 2, we find Pn as relation between special vertex values of suborbital graphs and continuous fractions. Cn is a series. Tn Cn can be written as, and if we take Cn equality 0, we find this vertex. And if we take Sn equality infinity, we find this vertex. Nth vertex in the path with minimal length in the suborbital graphs F1 with the recurrence relation, we can write as, from here we obtained this matrix, and it is an element of a modular group. From here, we found this equality. Relation between vertices of suborbital graphs and Fibonacci numbers. If these conditions are provided, we obtain Pn as. From here, we obtain lemma and theorem. Relation between vertices of suborbital graphs and Lucas numbers. If these identities are taken into account, we obtain it Fn as approximation value. If the last approximation value is substituted in the identity, it becomes. From here, we obtain it Pn as approximation value. From here, in the suborbital graphs Fn, the representation of this vertex with Lucas numbers is found as. On the path with minimal length, starting with the vertex, with this vertex, then these identities are found for the matrix, for this matrix. And if the values are written into the matrix, we obtain it this matrix with Lucas numbers. Using this identity, these numbers can be written as. If we take these values, we obtain it this matrix with real numbers. If we take these values, we obtain value of the 15 vertex with real numbers. Lemma, in this lemma, we obtain it determinant of this matrix, and we found one proof. In this lemma, we obtain it a determinant of this matrix proof. In this lemma, we obtain it a value of vertex with Lucas numbers by using this equality. In this lemma, we obtain it this identity by using this equality. Lemma, in this lemma, we obtained this identity by using Pn. Proof ln is obtained from Pn. From here, we obtain these identities. Then L2n is found as lemma. In this lemma, we obtained this identity by using these identities. These identities are obtained from Pn. There, if we add these identities, we found this value, and we know that this identity is provided. As a result, Fn is obtained as. In this lemma, we obtain it in this identity by using these identities. Lemma, in this lemma, we use it. In this lemma, we obtain it this identity by using approximation value of Fn, and we obtain it 0. In this lemma, we obtain it in this identity by using approximation value of Fn. These are references. Thank you for your patience.
Okay, we thank you, Professor Gokcan, for his nice talk. If there is any question or comment, please use the question and answer button of Zoom.
Thank you.
Let me check the question answers session.